Hi, and welcome to our next session here in our Bayesian optimization chapter. Here I will talk about the basic loop that goes on in Bayesian optimization. So we'll not really discuss acquisition functions, but we'll discuss all of the rest, at least touch upon it. So let's remind ourselves what we actually want to solve. So we're given this black box here, this C of lambda, which is our cost function based on our configuration vector lambda. We don't know its analytical structure, so we basically have a computer program in front of us that we can run on a configuration vector lambda, and we can evaluate that. So it's a black box, usually an expensive black box that we can query at given configuration points lambda. For now, in order not to overcomplicate things, we will assume that these evaluations are noise-free, so that the evaluation is pretty much exact. I guess you can get that if you have validation data that's quite large, if you're willing to resample, cross-validate your score, your performance metric quite a lot with many iterations, or I just don't want to deal with this overcomplicating aspect of noise for now. So I'm assuming that either there is no noise or it's so low that we can actually ignore this here for now. In terms of, we already discussed the most core idea of Bayesian optimization, and that there's an archive of past evaluations. So I'll call this capital D. And I will put my evaluated configuration costs pairs in there, usually indexed by T, and the size in a certain iteration of this archive is denoted with a capital T. And the idea is to use this archive to learn as much as possible about it regarding the relationship between lambda and the output value, the score, the performance metric we're interested in, and to plan subsequent evaluations intelligently, so that we can optimize our cost function as sample efficiently as possible. I'm going to use a simple one-dimensional toy example here in the upcoming slides. You can see this here. So this is a simple, toy function that I've created. I'm not the biggest fan of these 1D examples because they are sometimes a little bit misleading because they are so much oversimplified, but we need something to visualize. So I guess this is a good idea. Sometimes I'll at least try to also visualize stuff in 2D. We usually care a little bit more, about BO's performance beyond 1D or 2D toy examples, but I somehow need to visualize the algorithms in such a university course. So I guess, maybe we can live with that. So the first stage of Bayesian optimization is usually called the initial design. So we need a first batch of evaluations before we can fit any surrogate, right? So in order to do machine learning, we need some data to fit our model on. And the idea is that this initial design should cover and explore the input space as much as possible. The whole idea is that, we have no model at our disposal because we need this initial data to fit our first model. So what we usually do is just some, space covering exploration of the configuration space. So the easiest choice would be something like a random design. Just place points uniformly at random into our configuration space. There's stuff like Latin hypercube sampling or, quasi-random Sobol as sequences and so on. Usually the type of design does not have the largest effect on Bayesian optimization performance. What is usually a little bit more important is the size of the initial design. This is also, there are no perfect rules to determine that. The trade-off is usually if we pick a design that is a design size, which is too small, then there's going to be a bad initial fit, and our optimization might even go astray, so to speak, at least in the first iterations. And the model we are fitting in the first iterations can be somewhat degenerate, so to speak. And if it's too large, obviously we are now wasting our budget before intelligent optimization even starts. So we want to be somewhere in between there. So as a rule of thumb, maybe take something like 4 times the dimension of your search space as a minimum. Some recommendations are even a little bit higher, up to 10 times D, but this can or already be quite a lot if your D is not too small. So I don't want to go too much into the details of initial designs now. I'm not going to cover Sobol sequences and so on here, but I'll at least explain Latin hypercube sampling because you can do this in 1 or 2 slides. So Latin hypercube sampling actually partitions the configuration space into bins of equal probability. So I've done this here for 2 hyperparameters, lambda 1 and lambda 2. And the goal is now to attain a quite even distribution of sample points. And one way to measure this is to look at the histogram of our projected 1D marginal distribution, so to speak. And of course, in theory, these would also be uniform for random design, but in practice, you can see that they vary. Yeah? And we want to have these as uniform as possible, even for the empirical versions. And the idea now is to look at these bins here and to allow at most 1 sample per bin and to have exactly 1 sample per row and per column. And this is how this Latin hypersquare is now exactly constructed. Yeah? You can see in each row and in each column, in each associated bin, we have exactly 1 sample, which gives rise to these, perfectly uniform empirical marginal distributions. And how you place the points in each of these in these bins, you can do this either uniformly random again inside of the bin, or you can just use the midpoint. So yeah, here for the LHS example, I've placed them exactly in the middle, as you can see. You can create actually quite a lot of these 1D, not 1D, of these. You can actually create a lot of these different LHS designs here. Yeah, of course, there are lots of these, plans you can create that have this property of having exactly 1 sample per row and column. So usually you want to have like an extra criterion to pick a specific LHS design. And one way to do this is to use the so-called maximum criterion. And that's also quite easy to explain. So we just take a given design, which consists of a couple of points spread out in our configuration space. And then we measure the minimal pairwise distance for any distance metric in this space. I don't know if this is just numerical parameters. Usually this metric rho is something like Euclidean distance. And then we measure the minimal distance between any 2 pairs of points. And as you can see here, of course, this is now, I guess it's exactly what it just said. It's this minimal distance between design points. You can also see this as, a packing radius. So the radius of the largest ball around each point, such that no 2 balls overlap, if you want to have like a more geometric intuition for that. But it also makes a lot of sense now to pick the design plan D that maximizes this minimal distance between any 2 pairs of points, because this drives all of the configuration points in that plan as far apart as possible. And if they're very close together, you're nearly running the same experiment. So if you want to, have a plan that explores your input space very evenly, very uniformly, very space-fillingly, so to speak, then maximizing this minimal pairwise distance seems to be quite intuitive. If you would like to solve this optimization problem here optimally, unfortunately, that's a combinatorial problem. Usually we solve that heuristically. Usually we also don't care about solving this perfectly because we don't need perfect initial design plans, so to speak. So sometimes people just look at many different LHS designs in a random search-like manner, and then they just pick the one that's best in terms of this minimal distance. Or you can also run something like a simulated annealing approach by doing, column swaps or so on the plan. I guess that's also quite intuitive how this works. Swap columns here for points, and then in a simulated annealing manner, you optimize this Q criterion here. Okay, so after initialization, we can now really start with the main parts of our Bayesian optimization loop. And as I've already said, the main idea is to now fit a regression model to our historical data, to our archive. Then After that, we would now like to extract as much information as possible from this regression model to plan our subsequent design point or points. If we can evaluate our cost function without noise, we'd usually fit an interpolator. Yeah, so if there's no noise, we can directly interpolate through our design points, and that's what I'm going to do here in this visualization. And you can see this here for an initial design of 4 points on this 1D toy example. Now, instead of optimizing the expensive C, I can optimize my cheap surrogate function C hat. I would obtain some proposed new point, which is simply the minimum. So my default is always to minimize costs here. You can see there's a red point here, and that would be proposed, and I would evaluate that now. Of course, my surrogate model is predicting that that point will have a certain performance, a certain cost. Of course, this is not perfect. It's just a guess. It's just a prediction. And the real evaluation will look somehow different, as you can see here on this plot. Now, we adjust our model in terms of the expanded data set. So there's a 1 point more now in the archive. We update our model. We can do this either by complete refitting on the archive data, or we can do some form of a cheaper online update of our surrogate model. Then we would optimize our surrogate again, get another proposed point. Again, we evaluate that. And again, we update or refit our model. Again, we propose a new point. We evaluate that point. We can see, okay, this is now exactly on a design point we've seen before, at least visually here in 1D. At least it's very close. So nothing has changed too much. And now maybe we might assume that our algorithm has converged. So I guess in a practical sense it has. So if I would run this now for more and more iterations, exactly in this setup here that I'm using for the slides, nothing interesting would happen anymore. Unfortunately, let's remember how our real cost function C looked like. We now ran straightforwardly into a local minimum. And the reason is that we didn't really explore the most crucial areas of the search space. So if you look into this area here, you can see that we placed some points there, but we did this in a very coarse manner, and just by, bad luck, these 2 points here were also placed in regions where the cost function has very bad and high values, and we never really explored this region here. And then because our surrogate model reflected that in terms of its prediction function here, what you can see here, we were assuming, we were predicting with this surrogate model that all of the function values in this area here are quite bad. And this leads us to the insight that just optimizing this mean prediction here of our surrogate model is probably not a good idea. This would give rise to something which we would call pure exploitation. So we are only placing points in regions whereby, or due to the surrogate model and its predictions, we think that the cost function is quite low, but we would not explore unseen areas of the search space. And for that reason, what I've just shown to you is not really what we would usually call a full Bayesian optimization variant. I guess we could do that, but we would have to, very transparently say that we are not using something like a true acquisition function as expected improvement, but we are using the posterior mean here as acquisition function. And that's usually not a good idea, exactly for the reasons that I've outlined here on this slide. There are smarter proposal rules called acquisition functions, and we'll cover them in detail in an upcoming session. And these actually really reward our Bayesian optimization algorithm for placing points into unvisited regions of the configuration space. So let's do a quick summary of what we have learned here in this session. So the basic Bayesian optimization loop works in the following manner. So we create an initial design. We then fit a surrogate model on the archive. We propose a new point, lambda, capital T plus 1, by optimizing the acquisition function. What that actually means, we haven't really studied yet. And then we evaluate our new proposed point with our expensive cost function. We update the archive, and then we iterate from step 2 on until we have converged, quote unquote. Usually this is quite hard to detect or let's say until our allocated computational budget is exhausted. Yeah? The core design choices of such a BO and BO algorithm are partially which initial design we use, which surrogate model we are using to fit our unknown cost function, also this rule we use to propose the next point, the acquisition function, and exactly through these choices here and their details we will now go in the upcoming sessions.